get out some paper and a pencil and work along with me. This is going to start out kind of boring, but it's going to get much more exciting as we go through. To evaluate the definite integral from 0 to 1 of t by interpreting the definite integral as an area, let's first start by just drawing the graph of the function t from 0 to 1. So this will be the t-axis from, say, this is 1 here. Well, the graph just looks like this. Okay, so it has a height of 1 when t is 1. Now, this is just a triangle, and so the base is 1, the height is 1, and so the area is 1/2 1 times 1, which is 1/2. So this definite integral is 1/2. Where it gets more exciting is if we say, well, let's keep this 0 here as 0, but let's change that 1. Let's expand the graph of t a little bit here. Instead of the upper bound for the integration being 1, let's say it's some number b. Then, because the function is just the output is the input, f of t is t, so when t is b, the output is also b. Now, I can look at this. This is a triangle. So here, I'll say the definite integral from 0 to b of t with respect to t is, look at the blue triangle. It's got a base of b and a height of b. So this is 1/2 b times b. In other words, b squared over 2. Now, there was nothing special about me choosing the letter b here for the upper bound of integration. I could have chosen a or c or d or any other letter. I probably shouldn't choose t, though, because t is used in the definition of the function. However, I could replace that b with the letter x. So let me just highlight every instance of b, and then I'm going to replace it with the letter x. Let's see if I can do this. Okay, so we have an x here and an x here, and we'll replace that with an x. We'll replace these with x times x, and so now we get x squared over 2. Now what we're saying is the definite integral from 0 up to x is a variable here, it could be any number we want, the definite integral from 0 to x of the function f of t is t is x squared over 2, the area of this triangle. Now things get really interesting if, let me just move this over here a second, if we give this thing a name. Look at this over here, x squared over 2. That's an expression involving x. I'm thinking of x as a variable, and so I can call this a new function g. G of x is the area under the curve from 0 to x. I'm going to say that again. G of x is the area under the curve from 0 to x. X is the input. It's the upper bound of integration. The output is the area under the curve. In this case, the output is x squared over 2. So let me just write this down, the left and right hand sides of that whole string of equalities here. G of x is x squared over 2. Now what's really neat to notice is that if I take the derivative of this new function g, the derivative of x squared is 2x, and I have a 2 in the denominator, so those 2's will cancel, and I'm left with precisely x. So the derivative of g is a function that takes an input x and gives you the output x. Now, that's the function, actually, that we started with. The function we graphed over here was just t. It takes an input t and gives the output t. It takes the input t and gives the same number as the output. It's no coincidence that the derivative of g of x here, defined in this way, is in fact the same function. Using different letters, here g prime of x is x. It's defined in terms of x and not t, but it's the same function. It takes a number as an input and gives you that same number as the output. That is the first part of the fundamental theorem of calculus.